All right, everybody, welcome back. Right now, we're going to hear Leopoldo Sarra talk to us about autoformalization in physics and engineering, which is, kind of outside of the realm of our normal things about just mathematics. So I look forward to it. Take it away.
Thank you for the introduction. I'm Leopoldo Sarra. I'm from Axiomatic AI, and this is a startup based in Boston and Barcelona. And what I want to talk to you today is like the projects we're working on formalization using Lean, and specifically for physics and engineering. So first of all, I would like to thank the organizers for having me today here. And it's true, it's like slightly outside of math, but I think there's a lot of potential for Lean to also expand outside of this domain and move also to more applied domain. And this is what we're interested a lot in doing. And we're happy also to work with the community in developing the missing pieces for this. So just to give an idea of what the problem I'm thinking of is there's a lot of enthusiasm right now in mathematics, right? And formalization for mathematics. And the question is whether we can have the same enthusiasm also for physics, for example, and other, let's say, scientific subjects that make some rigorous and formal arguments, right? So every time there is an argument that is logically consistent, we can think of a way of formalizing it and verifying it with formal methods, for example. And this is especially useful in the age of AI because as like we have agents and LLMs that can propose arguments, it becomes very important to be able to verify them. And we believe that formal methods could be one way of doing this. So an idea of why it could be useful in physics, and I think this is easy to imagine, right? Like you can make a scientific derivation and many times it can be wrong, right? So many things in physics come from experiments, right? And so you cannot predict that. But some other things come from your scientific derivation, from the derivation of your theory. And in that case, these are the cases where using formal methods can help. So a standard example could be like the theory of metal conductivity that was proposed, for example, by Drude in the beginning of the century, the past century, right? And this was actually wrong. But and the reason why it was wrong is that there were two different effects that were modeled the wrong way and sort of compensated. But another reason why the experimental results appear to be sort of in agreement with this theory is that there was a calculation error as a factor of two, right? As a factor of two. And if one had verified the calculation, for example, this would have been detected earlier, and this theory would not have been accepted and influenced like many physicists for more than 5 years, for example. And this is just an example to say that it's true that in physics many things are empirical, but it's also true that there are cases where theory comes first and you want to model theory and verify the theory that you make based on the assumptions that you have in physics. And formal methods indeed have been used in physics in some cases, right, and in other sciences, but I would say not very systematically, right? So you can imagine that there are some papers using different kinds of theorem provers, right, and many different fields, but there hasn't been like a systematic formalization of physics. Now there are some projects like PhysLean, right? And before it was high energy physics Lean, and these I think are very interesting for this direction. But what we are mainly interested in is the practical approach. So rather than just collecting a lot of scientific results, it's also making usable and applicable in practical setting. So even if you are like you are making an application, you're using some physics derivation to make some argument, it would be great if you were able to verify this argument using a scientific framework provided, for example, with Lean and using formal methods. So what's the reason why this would be very interesting? Because you can track all the assumptions and approximations that a physicist would usually make, or an engineer, like making sure that all the approximations that you make sense, are traceable. And also you can ask yourself what happens if you drop one assumption or if you make some change in some other assumption, what will happen? Will you still be able to prove what you want to prove? And you can also identify errors in some derivations that you may think that are correct. So the scope of this talk is to give you an idea of the direction we are trying to push forward, and also informally discuss like what can happen, like what can come from this direction, and how feasible it could be by using lean and formal methods. So I just wanted to give you a few other examples of past discoveries that happen from the theory itself, and then proved experimentally, rather than being first shown experimentally and then justified by theory, like deriving like electromagnetic waves, right? This was one term that you could imagine existing and having these results by looking at the equations, right? Or like the discovery of antimatter, right? Like looking at negative energy solutions of Dirac's equation, right? And also there you can discover them by analyzing the theory in some sense. And if the theory is formally encoded, right, you can make this study much more rigorous and precise. And same for the like discovery of the neutrino, right, by analyzing conservation law. So what I'm pointing out is that right now in physics, there's not a consistent library, right? Like there's some efforts like PhysLin, right? There are some libraries like quantum information, but there are some sort of different needs with respect to what you would like to have in MATLAB, for example, right? Because it must be much more specialized in some sense, right? And you need to encode many things that in mathematics are not so rigorous. So discovering and inventing ways of sort of making rigorous what many people would agree on, but that said like this, like making a Taylor expansion, right, or making a first order like derivation, right, like you would agree as a physicist, but you could encode mathematically and make it formally correct. It just needs to be done the right way in some sense. So it would be quite interesting to have such a community of physicists, right, and mathematicians that are interested in like making this kind of progress in science. And this is what we are interested in. So essentially, the PhysLin project, for example, goes in the direction of making a universal physics library, right, containing many different results. But I think also that building the tools that enable this kind of scientific reasoning and building the tactics that make essentially allow you to use formal methods to reason the same way a physicist would do, right? So making the kinds of approximation automatically rigorous in some sense would be quite useful to the community. So as I was saying, I'm working currently at Axiomatic AI. This is a company founded by several professors, physics professors from MIT, ICFO in Spain, and Toronto, and currently led by Jake Taylor, that is previously a professor in Maryland and worked at NIST. And we're generally interested in this kind of like verifiable, trustworthy, and interpretable AI systems for science and engineering. And what we are interested in doing is developing formal methods for science. And we have also a team doing formal verification, and particularly formal verification of science. We have a multidisciplinary team composed of many mathematicians, physicists, and AI scientists, and lean experts. So what we are currently doing, so this is a project we have been working on for the past 6 months, and mainly a scientific project. So we are interested in making it open source and sharing it with the community and develop it openly, right? Is a proof of concept where we are thinking of quantum mechanics, for example, because it's one field of physics that is sort of easier to formalize because it has already been taught since the beginning in a sort of formal way. And we would like to build a library that is sort of usable for applications. So instead of just collecting quantum physics facts, we're working a lot on building also a data set of formalized exercises that make use of this library. So we would like to have like a way to use a library, but also build exercises and check these exercises using the library. And this is sort of goes toward the direction of having applications to physics. So it's like you have a problem and you can try to formalize it, perhaps using AI tools, but then you can use like an existing physics library that supports the formalization and the implementation of these specific solutions for your problem. And if you don't have this, right, it is right now, you always need to start from scratch, right? You need to define each of the concepts in physics. You need to make progress one by one. And so the difficulty that you have in formalizing even a simple problem is huge, just because you're missing like the units that are not integrated in any like bigger package. There are some options, but they're not standard in some sense, right? You don't have perhaps reference frames. You don't have like derivatives with a specific like coordinate system that you would usually use in physics. And so adding essentially all this infrastructure that would make simple, even perhaps for some non-human friend, right, to be able to formalize it appropriately. So essentially, what we're doing is that building this kind of proof of concept in quantum mechanics, and also interested in expanded it to other fields of physics. While of course, as a startup, like the commercial application that would come from there would be like proprietary. Like we plan to work with the community on the scientific part, essentially. So as I was saying before, like what we would like to have is this library where we can use for specializing it for every specific problem. So this library will have general physics theorems, and you can then use them to show some results of some specific problem, and then in practice check the assumptions and make sure that the derivation of a problem makes sense in some sense. Yeah, so as I was saying before, we're very interested in integrating ourselves like in existing efforts like Fizzlin, but we also want to build the missing pieces that allow the practical use and concrete application. And there's still a big open question, right? Like I will talk briefly later about the experiment that we're being running. The question is, how would it be, how feasible would it be for systematic adoption? Like if we want to imagine that a theoretical physicist, right, that makes some derivation about something starts to also include like Lean code in their paper together with the code for some simulation, right? Like how far away are we? And would this make sense at all, right? Is it too hard to formalize this part of science, and it's too different from math for being formalized, or is it something that would actually be possible and perhaps it's just a matter of time from when like also scientific arguments will be formalized? And just to be more concrete, like imagine like you have a problem like this, not only you have a library, but when you have an exercise like this, find the probability distribution of the particle coordinates, mean value and standard deviation, you want to be able to have objects to use in Lean and to essentially solve this exercise, right? So this is the kind of problem that we are looking at in some sense. And we want to be very test driven. And as I was saying, like another part of the puzzle is also developing tools and integrations and use perhaps AI and workflows that can help doing this. So the problems with respect to a math formalization project is that the formalization part is often very weak in physics. So you need to really identify the right way of formalizing something. Perhaps it's not in your physics textbook, but it's in some other mathematical physics book. You need to identify. You need to write down all the concepts that are missing and create a real blueprint of what you want to formalize. That is sort of harder to find than in a mathematical project, right? Then you want to formalize it, then prove it, and then understand which part should take in the library, right? So there's a system design challenge there that starting from scratch is definitely not simple, especially like if as physicists we start that we are not a strong Lean developers in some sense. Right, so having the insights of something that would be general enough to be reusable, but also not too general that will be too hard to use. So that's just I want to show a proof of concept. So imagine like you have a problem like this and you want essentially to interpret it, right? And we can go faster. And what you want to do is sort of create a sort of blueprint, right? Where you extract the concept that you want to use and formalize. And then you run perhaps a prover, like one of your favorite provers, which of course should not work just on competitive math, but should work quite outside of the domain in which they're trained on, because we will talk about physics, we will have other kinds of concepts that they will never have been encountered in the training set, right? And so this is a sort of challenge where in our experience, agentic solvers like that can explore your library tend to work much better. And they have been looking into this, and we may release something later this year. And yeah, so this is sort of the workflow we are trying to explore and implement. So this is similar to many other projects, but the main necessity that we have is to be in a sort of different field with respect to math, and most of all, use a library that we are developing at the same time and learn the concepts and reuse them, and essentially also understand how to structure this library so that you can reuse it and build the exercises. Right, so then, for example, in this case, we end up with this theorem and we can make the proof, and we're able to prove this exercise by making use of some other concept that we put in the main library. Yeah, I think that's sort of the idea of this demo. So I cannot show yet much more because it's still a lot of work in progress. Like you can imagine, we started a few months ago and we are still like getting started, and we plan to work much more on this. So this is just an informal talk. So I'm very looking forward to learning more about like the thoughts from like Lean community and like some comments or experience by some other people that already tried other formalization projects. And I was saying we already started making some works on understanding like how provers can work outside of the domain of math. We've been working also in this collaboration on SorryDB. So this is a data set of sorry that statements that come from the GitHub reservoir. So the GitHub repositories that are actually Lean packages on reservoir. And this will be like essentially a data set to understand if provers can work also outside of the math domain. So just take some sorry and try to prove and see how well the various provers that are available right now work. Then we want to work some proof of concept to show that it's actually possible to do in physics the same that is being done on math, but with some practical approach. So showing that it's like in MATLib, this is a reusable library that you can use in many different projects. We would like to have a library in physics that you can use for many different applications. And we are interested in seeing like which AI tools and workflow we can develop, also integrating with the other tools that exist, but make the process like more usable also for perhaps physicists that are not expert in lean and formal methods. So trying to reduce the entry barrier so that more people can collaborate. And yeah, so this is mainly what I wanted to tell you, and I'm looking forward for more discussion. And in case you're interested in this kind of project, like we're really happy to talk and discuss potential collaborations, even not necessarily within our company, right? But also just from the scientific perspective. So thank you very much, and looking forward for questions.